says compare the delay of CPA 8 and CPA, find speed up as the ratio of CPA 8 divide delay of CPA 8, delay of speed up. Delay of CPA by CLA. Increment. So this is one of the parameters we're going to talk about in the next chapter. So it's giving you the equation here. CPA, carry propagate, we know that it's a whole bunch of pole ladders like that. And if you remember, the carry was the fastest. You have to look at that. So the delay of CPA 8 was 7 delta of pole ladder carry plus delay of the pole ladder itself. And pole ladder is force. Oh, this was using NADs. So NADs are shorter, so 0.2 nanoseconds plus 0.3 nanoseconds comes to 1.79 nanoseconds. Delay of CLA 8. CLA, you know that it has a PG unit, and then it has a CG unit, and then it has a sum. So X4 was the longest. Here is the 3.9 seconds. Here is Mariana X4, 0.3 nanoseconds. So you add it up together, you get 8 nanoseconds, 0.8. So this is 0.8 nanoseconds. So speed up, this is only for 8-bit. So it is 1.7 nanoseconds divided by 0.8 nanoseconds. So that comes to 2.125 nanoseconds. You can see that if you make that bigger, it's going to be a lot faster. Second question, 3.8. It says design with 8 to 1 lux using 2 to 1 lux. Now we can't design 8 to 1 lux just using sum of product. That's going to be fan in and fan out violation or very close to it. So you have to use a tree structure. Cross-sub elimination, okay? Cross-sub elimination. So you probably have heard that. So you take 2 at a time. So you take 2 at a time, and it's called cross-sub elimination. So if you take, so you put the numbers here, x0, x1, x2, x3, x4, x5, x6, x7, and then you connect all of these to same input, like S0, 1, 1. So if you're looking for 6, so S equal to 0, this is gonna produce x0, this is gonna produce x2, x4, this is gonna produce x6, and then you put those into another 2 to 1 lux. And then you send S1. 6 is 110. So 1 1 is gonna pick this one, which is x6. It's gonna pick here and x2. And then you're gonna feed all of this into another 2 to 1 mux. 0 1. And this would be x2, which is in this case 1. So it's gonna give you x6. So that's how it works. It's a log 2 number. So delay is log 2 times the delay of number of muxes you are using.
So is it log 2 8 times the
No, it's going to be log 2 of 8 times delay of 2 to 1 mux. So that's 3 times mux is also mux is 0.3 nanoseconds, so it's going to be 0.9 nanoseconds.
That was cool. If you put that in the logic system, you could sit there and select the bits.
Yeah.
And see it actually all this bit.
Yeah, exactly. But still working on. We have purchased LogicWorks. LogicWorks is much easier to
This
use.
is easier than the.
Super easy.
This is like what I.
Yeah, it's super easy.
But that was the only way I could understand it.
That's fine. LogicWorks, you can make a module and then just work with the module as opposed to gates. They are trying to install it. I don't know. Something is going on. I guess everybody's trying to update. There's a deadline for Windows 11, right? It's coming up.
Yeah, even the Office software now, they're doing the same thing.
Yeah, Office sucks.
And now I think they're trying to make it all cloud-based.
Yeah, well, whatever. I mean, files that I have work. They are not. I can't produce PDF. It gives an error. Font problem. So, as I said, Microsoft has a monopoly. So, no matter what they do, we have to stick with it. So anyway, so that's how that works. So, the last problem is delay of the. This is probably was the hardest. For this one, I think we need to go over the design, so you'll see how we are calculating the delay. You have to look at the longest path. The longest path. We are using it on that.
Okay,
It's over here.
for this problem too, right?
Yeah. I guess. I think we would, CLA 8. So why does that come? Okay, so delay of this comes out. The other path is through the flag, through the mask, and out. That's another one. I think in this case, this delay, flag, and this are pretty much the same as the delay of that. So you have to, and then you have to go to the add module, arithmetic module, and see. Correction. Arithmetic module. So here is the adder and subtraction, which is merged into this. So the adder and subtractor has XOR, the adder subtractor, and the overflow. But this is going to the mux to come out, and this is going to the mask to come out. So you have to look at which is the longest. But I think in this case they both are the same delay. Okay. So inside that adder and subtractor, it's this particular thing. So let's go back. double-sided mux, it says use 2-to-1 muxes. So this is a 2-to-1 mux. So each one is 0.3, 0.3, so it's 0.6. 0.6 delay for this. And then let's see what else there. Okay, this one kind of shows the details a little bit. And then in order to do subtraction, we have to use not subtraction, but increment versus adding or subtracting b. We also need the mux over here. So this sorry, it's not shown on that one. Let me go to the next page. So this module that has a export to create the adder subtractor. We need to add another mux to do the increment. So it's going to be this plus the 2's complement adder subtractor, and that goes into the mux. So if you have to write the answer down, so it's going to be like this. So this is the problem. 10. Okay, so I can write it in. So the delta of mu is delta of map plus delta of arithmetic unit plus delta of 2-to-1 mux plus delta of 4-to-1 mux. It's always better to write like an algebra. Write the variables and then stick to the numbers. It's much easier, not only for understanding how things are, how we do it, but also you writing the path, and if you make a mistake in the arithmetic, it's not won't be a big deal. But if you don't put these things and you just put numbers and get the arithmetic, it will be confusing and might end up losing more points. Okay. So what is the arithmetic part? This one. This one, if you
And that's just a CLA 8 for the arithmetic.
this one has delta of G unit, delta of G unit, delta of sum unit, plus the delta of XOR to do adder and subtraction. This is used for add and subtract. And this is just the adder. Okay, remember we have to invert the bits. Exam 1. When we are doing A minus B, we have to do A plus minus B, 1's complement plus 1, right? When we flip the bits, so that's why we use XOR to flip the bits.
The last one you named that is after sum. What was the name of that delta? That was delta inverted.
This 4-to-1 mux.
The one below. I'm sorry.
XOR.
It's just delta XOR. Okay.
This is XOR. So if you remember, we had an XOR and use the adder to create an adder subtractor. And adder subtractor is on A plus. We had a question in the midterm minus B in 1's complement, which is flip the bits, and then add 1. And the add 1 comes out as a carry in. So we are not using 2 adders, we just use 1 adder. This is just as a carry in. Okay? So that's, if you add up those, you're going to get 0.3 nanoseconds, 0.2 nanoseconds, 0.3 nanoseconds, 0.3 nanoseconds, and if you add all of those, you're going to get 1.1 nanoseconds. So now delta of U is going to be here So here's the map. This is the circuit for the map. Now when you're calculating, you can look at the longest path. Okay? But the simulations, all that stuff, they show that this can be done. It's really depending on this signal to start. The others are coming later, so it doesn't matter. So the add or subtract is really, even increment, decrement, really waiting for this signal. We're just incrementing or decrementing, so it's really 0.1. But you could look at this and say this is the longest, 0.1, 0.2, 0.3. It won't be wrong, it'll just be a little bit slower, but then simulation will come up and say this is what it needs. That's why they do simulation, including wire delays and things like that. So if you put 0.3, it's fine. If you put 0.1, it's fine. I've already given instructions to my grader not to take points off on those. Okay? So, and the flag is 0.3. And then we know that overflow is also XOR, so it's a 0.3. So 0.3, 0.3, 0.6. This will be 0.6 as well. So both of them will come at the same time. It all depends on, it may be that the mux will be faster because we are just looking for the S2. Anyway, so what's the answer? So if you use delay of the map, if you use 0.3, I'll just make a note over here. Could be 0.1. Okay. Plus arithmetic unit.
It's a 1.1.
That's 1.1 nanoseconds. Plus 2 to 1 mux is 0.3 nanoseconds. And then plus 2 times 0.3 nanoseconds for the mux. So 1, let me just go out of it. 1, 2, 3, 4. So this is 1, 2, 3, and this is 4. So you add up all of that, and you're going to get 2.3 nanoseconds, or 2.1 nanoseconds. Simulation will probably come up with this, but rough estimate is going to be that. Okay. So exams are based on the understanding of the assignments. If you understand assignments, as you saw in exam 1, you should be okay. So even though you may not have this correct, but now you know how we are determining the delay, the longest path. You have to look at all the paths and see which one is longest, and then just go through it. Obviously, the exam is not going to be this complex.
So if you got some of those in there, is there partial credit for that, or is it all or nothing?
No, there's partial credit.
Okay.
There's always partial credit.
So like I got the box and the arithmetic.
You have to compare if somebody leaves it blank,
Yeah.
where somebody does things which are in the right direction. Life is always partial credit, right?
I guess all of it is, huh?
Life is all partial credit. Nobody's perfect.
They forgot the math. figured that was already there by the time it was going into the arithmetic module.
But the math is starting
Starting there.
everything, right? Because that's where you're deciding which operations you want to perform.
That's right, but that's dependent on the user.
That depends on the instruction. In
Once
real
the
life, it'd be
instructions
instruction.
started to do that
Yeah,
operation.
instruction, you have, I don't know, you guys, you do, definitely you know the assembly, like
Yeah.
R1, R2. This is gonna be part of the field, right, which is called opcode. So that is gonna go to the map, and the map is gonna say which signals to generate.
Yeah, I didn't think of that as a delay. That's, yeah, it is in there.
That's how
Yeah.
they do it.
Where's the 4 to 1 come from again? The 4 to 1 mux?
4 to 1 mux.
Yeah. Thought we can't.
You see that mux over there?
Yeah, I thought we split them into two 1 mux and big.
Yes. So that's why it is 2 times 0.3. Two muxes and then one, like a tree, right?
Yeah.
Like this one. It's only this portion. This is the 4 to 1.
Yeah, so the longest path is like going 2 of them, right?
Yeah.
Yeah, but when you add another 2 to 1 mux.
That
That's
is
the
for
math.
the adder. The adder to do increment, decrement.
Oh,
There's a mux there.
oh, that's.
So there's a hidden mux in that arithmetic module on top of the math mux.
Yeah, yeah. I mean, we went through that. I'll get to it. Well, the purpose for this, for you to go and really look at the details. So there is this is already embedded in the 1.1 nanoseconds, the XORs. But then you come to do the so there's that mux right there to increment or add B. So this problem meant to go inside and try to understand the whole ALU and figure it out. Okay, question, homework number 6.
Professor? Yes.
No, sorry.
So for the H1 mux, can S0, S1, and S2 be put through a NOT gate in parallel? And then you can get a delay of 0.7.
Put it through NOT gate.
Yeah, well,
Why would you want to do that?
the 2 to 1 mux is two nans, and then SEs go through a NOT gate, right?
Yes.
So, can't all 3 of those S's go through those NOT gates all at once at the start? So you only count 2 nans for each of the following 2 to 1 muxes?
Well, the map is determining those, right? Isn't it map is determining that?
Oh, I was talking about 3.8.
Well, they have an equation that we're supposed to follow.
Oh, 3.8.
Okay, something.
Oh, you mean this one?
Yeah.
And you're saying that put a NOT gate here?
Well,
Well, this is not just tailored to, it's not just tailored to one problem. I mean, this is just an example for 6. If you have 2, you're gonna have to put 0, 1, 0 to get the 2 out.
yeah.
So, I'm having a hard time to understand your question. You wanna repeat that?
I could,
That was the question we asked you on Tuesday.
What?
It was, because each mux has a NOT gate in the front. If you set all of the selector values simultaneously, then they'll go through the NOT gate all at the same time, so it works. Right? Yeah.
Is it like this one, I have
you need to count for the first one.
Is that what you're?
Well, we're talking about, you mean the design of the mux?
Yeah.
Yeah, there's a NOT gate.
But the NOT gate, like, that can happen before
knock gate doesn't have to wait for the muxes before it, so wouldn't you not count it when you're adding on top of those first muxes?
So you only
But
count
it's,
not
well, it gets counted by saying it's, 0.3. Now, estimation, I think the confusion is estimation is different than doing the simulation and running the system.
Okay, so we should be doing an
So
estimation.
it's difficult to say, okay, what's gonna happen? So you just look at the gate delays and just add those. This is an estimation.
Because you might get the selectors at different times.
Different times, I mean, the wire length and all this stuff might be different. So the best you can do is just look at the gate delays and then say, this is what it is. And then once it is put together inside the chip and all, well, modeling it, software, simulation, putting the wire delays, like every foot is like 1 nanosecond or something. And that's why they advertise things like 3.5, whatever, or 5.7 megahertz or gigahertz. It's because it's an estimation, and then you have to run those, include the wire delays, all of that. And then environment, heat, cold, all of that, and then say, okay, this is what, for general purposes, this is what we're gonna advertise. Yeah, so you don't wanna go into really detail of signal traveling, because you don't know. The wire delays stuff, you don't know. You just know that no matter what, it's gonna go to this gate, and then the output is gonna control it. Okay. Was another question here? Okay, so, question, homework number 6. So, did anybody get close to this number, these numbers? You got close? Okay. If you miss something, I mean, you have to go and look at it.
I just do math.
Okay, question 4.4, homework 6. You had, now, it did say that setup time, clock to queue are 0. 0 down, so no delays. So we have something like that. The reset was active low. So it becomes, was active here, this is active, then it becomes not active. So that means that you don't care about the first one. D, so let's say 1, 2, 3, 4, 5, 6, 7. So D was here, then it goes to 0, and then it goes to which one did we do? QA or QB or both?
Just QB, yeah.
QB, oh yeah. Okay, so it's not a latch, it's a flip-flop. Okay, so, and it is a negative edge. So it's a negative edge. That. So what it does, you just look at the edge, and then you decide what the Q is. So it's gonna go to 1. So 1, it's gonna go to 1. So this is, and then it's not gonna look at it until next time. It's gonna go to 0, and then care until next time. It's gonna go up, and it's not gonna look until next time, and it's gonna go down, and it's not gonna see that either. So this is what we will see on the falling edge. It's gonna look at the value. Falling edge right there. Falling edge right there. Falling edge. This is still 1. It's not violating any of the rules. And then it's 0. It's gonna go. So what it does is that if all the wire delays and these things could happen with the wire delays and things like that. So it kind of waits, and as long as this period is so period will be from here to here. So that will be adjusted so that all these things can go and stabilize. Things like that. Okay. Question number.
Wait, quick question.
Yeah.
So for QB, it always starts at 0 because D at the start is already 1.
Yes, but the reset is active.
So,
Oh.
active load reset.
So you reset, you ignore everything until the next one. Okay, 4.5. So looks like this one is also active low. D. This one is positive edge. Okay. So D starts at 1. Somewhere around here it goes to 0. And then around 6 makes something like this. And then goes like that. And this distance is setup time is 0.2. And this one is also 0.2 nanoseconds. And it says setup time is 0.115 nanoseconds and clock Q 0.1 nanoseconds. So it's a rising edge. So we're going to look at QB again. So, rising edge. So it's resets 0. And come over here. It didn't write value here, but let's say it's not violating. Gonna go to 1, 0. Gonna go here. It's not violating. It's bigger than the range. Gonna go 1.
Does it go back down after it's settled? Because D is down then?
Yeah, I mean, I didn't yeah, at this. But no, it's gonna eventually.
It just goes, okay.
Yeah, here it's gonna go. To be accurate, here it's gonna go to 0. Thank you for. Okay, question 4.6.
That gave us a set of time of 0.1 for that one. The clock came as 0.2, and then hold time is 0.1, right?
Setup time is 0.5, this is 4.6. Clock Q is 0.2, and these numbers are clock Q, setup time are 0.15.
Sorry, I got mixed up.
Yeah, so,
That was wrong.
so, okay, so QV is gonna get to this point. QV is gonna go up. 0 is gonna go down. Come over here. It's gonna go up. But then this number, this is less than like Q, it's gonna start oscillating.
And just to confirm, that oscillates all the way out, right?
The only way you can stop it, you have to reset it.
Reset is one way.
No, but I mean, just go forever, because reset is not active. It's basically locked. And then you have to reset to start, but if that happens again, I mean, that's gonna. Okay, so it says we have a D flip-flop.
Yeah, 4.6, it says the setup time is 0.1 on this code.
4.6?
Yeah, right here.
But it never reset.
4.6 setup time. Full time. It's still the same thing. The setup time you have is 0.15. Yeah, it's still did the same thing.
some of the numbers are messed up. Okay, so this one, it says setup time is 0.2 nanoseconds. Clock to Q is faster than hold time, 0.1 nanoseconds. Maximum propagation delay, there is a, so the D has, so we have a flip graph. The clock, and then there's a circuit over here that is 0.3 nanoseconds delay, you know, whatever inputs it has, and reset. So we are trying to figure out what should be the clock frequency, what frequency we should run this. So this is the it doesn't say what it is, it just says propagation delay is 0.3 nanoseconds. So always tau has to be, so tau is the period, right? So this is 1 tau. Has to be greater than propagation delay, plus you have to add these setup time, clock to Q. So that means the clock, here the clock is running a little bit faster. It's running faster. So you have to slow it down. So by adding these things, we are slowing down the clock frequency. So that means this needs to be 0.3 nanoseconds. That comes right from here. In some cases, you have to calculate that. And then 0.2 nanoseconds plus 0.1 nanoseconds. And that becomes 0.5 nanoseconds. And the frequency is, when something is greater than, and then when you inverse that, then it becomes less than. Okay, just remember that. So 0 nanoseconds. So what does that mean? 1.5 nanoseconds means 10 to the minus 9 seconds. Okay? 10 to the minus 9 seconds. So that needs to go up. So this would be 1 divided by 0.572 times 10 to the 9 hertz. When you inverse the second, it's somebody's name actually, hertz. Okay, so that becomes 2 gigahertz. 10 to the 9 is 1 gig, and meg would be 10 to the 6. So that becomes 2 gigahertz. Somebody's name.
Where were you given the clock to Q on that?
It's great now.
You are determining the clock. You are determining how fast you can run this system.
Okay, I guess we were given the parameters of the start time, the hold time.
Clock is you're determining the clock.
Okay.
You find the longest propagation delay. In this case, it was given 0.3.
We were given, yeah, but we were never given thou CQ. Such CQ, we weren't given zero.
CQ is
It's greater or equal than whole time.
It's always so,
Whole
it's
time.
the same thing.
whole time is a little slower.
Okay,
So it doesn't matter. Whole time and clock to
so you could just fill it in.
Well, the numbers we give it.
I solved it without it and then with it, is that okay? Because I did zero clock to Q and then did it with one.
Wasn't there in the assignment?
No, I
I don't have the book with me, I just have.
Yeah,
it
here,
here.
the book right here, it didn't list it, so given the knee flip-flop. 1 nanosecond setup, 1 hold, and
Okay.
propagation nanosecond.
Yeah, hold is a little
Yes,
bit
it
bigger
is.
than clock. So if you're giving them hold time, just use this.
Use this,
clock.
this.
Yeah, let me, I think
Yeah, it's in the slide.
I can show you, go to chapter 4.
It's written in the book, I know where it is.
I wanna
Too.
find it here.
It's
Yeah.
the whole time
I'm
violation.
gonna show you something.
It's in the whole time violation.
There's a timing diagram somewhere. Yeah, right here, you see that timing diagram?
No, it's not.
Yeah, let me just put the name. You see right here? Clock the cue and hold time.
Yep.
See, hold time is just a little bit longer.
Yeah.
So it won't hurt anything, it just makes the clock frequency a little bit slower if you use hold time. So clock the cue or hold time.
Yeah, you have it on 153 stated too.
Yeah, clock the cue is just a little bit faster. I think maybe it's historically, these are result of accurate simulations. Maybe the whole time, that's what they used to use. And then clock the cue is better, so they're using.
So they
clock the
started
cue.
using that instead.
Okay, any questions? Yes?
Can you label it different? Would we label it different, like say like cycles per nanosecond?
You mean the end result?
Yeah.
They just say cycles?
Yeah, cycles per nanosecond, instead of like hertz.
Well, okay. So this gives you the time. So here you just say 10 to the 9, to the 10 to the 9 cycles. Is that what you're talking about? So you're asking of what are you going to label this, right? So are you going to convert that into the, are you going to do the math? It's going to be eventually 1 over a second. Right? So I'm just saying that when the second is in the bottom, and you do the math, instead of writing something second, because this is the denominator. 1 over top. So this is nanosecond. So it's just the name. Hertz means cycles. Yeah. Yeah. You could say cycles, but accurate name is. You've heard of gigahertz? That's where it's coming from. They don't say gigacycles. Right? So you're asking if you put in the cycles at homework in your homework? That's okay. This is just first class, and now you're learning. So next time put hertz. Okay, any questions? Everybody understood, right? I mean, let me graded. It's just that I'm trying to see who's in class. Cameron Isabi. So I assigned several assignments. They are shorter assignments. Trying to give you short assignments maybe once a week. Probably one of them is a little bit longer, but the others are shorter. So every finite state machine is going to have flip-flops, next state generator, and output generator. We went over this example. Figure out what it is for overlapping 1, 0, 1. So if we label the, so this is how it will be. You can just put a design like this, but this is how it will be implemented inside the chip. They don't put all the flip-flops in one corner and the combinational circuit in another. They're all kind of mixed. If you label them differently, so if one of you doing this labeling and another friend of yours is doing another labeling and they get different equations, doesn't mean it's wrong. So the way you label it, it's going to impact the equations. We talk about this for FPGAs, and then Mealy. I think we did talk about Mealy, where the outputs are on the
Say there's no.
And then this is an example where you're still going to need 2 flip-flops. So the questions, I think this is where we stop. So what do we do with the unknown states? So these are the states of the machine. Okay? But then we have some unknown states. So what happens if the machine goes to unknown state? One easy question, one easy solution would be to ignore it. Ignore it. That would be like putting don't cares. If it's A, B, C, if it is D, just don't care. That would be like a toy. You know, kid is playing with a toy, bangs it on the table, stop working, runs to mom and dad, just do on and off, it's working. Okay. The other one is making sure it goes, you just, you know, sometimes you go in combinational lock and you enter it wrong and you just wait for a little bit and then you enter it again. That's what it is. It goes to some wrong state, then it says, then you wait, then it resets. You know? So once you convert that, we did that last time, into a truth table, then you use the previous chapters, K-map and all this stuff, you don't cares, everything, and you come up with Boolean expressions. Okay. If you have a Mealy machine, this is a Mealy machine, you can always put if you really need a more machine, meaning that outputs is not asynchronous, it depends on the input, it's always synchronous. You put a flip-flop, it becomes a more machine. The next step are just some kind of counters, different kind of counters, 0, 1, 2, 3, 4, binary coded decimal, 0 to 9. If you're building a counter for people, you go to DMD, you see a counter, that's a BCD, right? So you create it like that. There are a whole bunch of gray code. Gray code is kind of interesting. They use for, I don't know they do it now, but when they were disk, like the magnetic discs and CDs and things like that, you put a 0, 1. You put mirror here, you get 1, 0. And then you put zeros over here, ones over here, put a mirror. These are mirrors. Look at the image. You put zeros and then ones after. This is called gray code. One of the disk sectors will label as gray code because when you go adjacent sectors, there's only adjacent thing, there's only one bit different. See, one bit different, one bit different, one bit different. So if the disk head goes a little bit too fast and gets over here, it knows it went too fast. So every sector will be one bit different. Instead of counting 0, 1, 2, 3, which normally you'll have, you know, sometimes it's not one bit different. You see, you have 3 bit different. So this gives you one bit difference. It had, maybe still has, but I don't know. I'm gonna skip this part where you're building from smaller counters, bigger counters. But here the next example is interesting. This is a counter, but we are not designing finite state machine. This is where we are going. So finite state machine is only for the smaller designs. For something big, you don't need to do finite state machine. This is a counter. See, there's an adder. There's an adder, which is always increment 1. And we have a 3-bit parallel load register. There's a 3-bit parallel load register, so you reset it, it's 0. 0 goes over here, gets added to 1, and through this box gets loaded back in. So 0 plus 1 is 1, loads in, counter now shows 1. 1, added 1, 2, counter goes, loads in, counter 2. So it adds like a binary counter. But it's not, is it finite state machine? Is this a finite state machine?
I wouldn't think so. It's just cycle, every clock cycle, just doing the same thing.
Does it have flip-flops?
It does have.
Does it have combinational circuit?
Yeah.
No. Adder, the box, those are combinational circuits. So it is a finite state machine.
It's just the
But we
states-
didn't design it using finite state diagram. Okay, and you can build it 8-bit, 16-bit, 32-bit counter. The adder has to be 8-bit or 16-bit, and then you have to have 16 flip-flops to build the register. Okay, so in fact, everything that only chapter 5 for a small design. Chapter 5, if you look at the chapter 5, we'll go to the very first page. We can remember this. Small designs. Sequential circuit, small design. This is only, your finite state diagram is only small designs. When you get to bigger designs, like CPU is a finite state machine, but it's not designed as finite state diagram. Okay? So,
Things like sensors, something that's not as complex.
something like combinational lock, which, in fact, I have assigned you some things as USB disks. USB has 4 wires, power, ground, and the 2 are just repeat of the same data, but it changes so that you don't have a clock signal. Okay? If you have a USB, it only has 4 wires. One is clock, one is power clock, and power, no clock, power, ground, then it has recording. And these 2 are pretty much the same, but it's a little bit different in terms of transition, so that you don't need a clock signal, but they can create their own, from here they can create the clock signals. So this kind of revolutionized everything. Before this, there was a 9-pin, you might know, cable, huge, very thick cable. Before that, it was a 21 or 24 cables in one. It was just heavy
Ample connections.
heavy things to carry around. Okay, life is just getting easier and easier, right? Now you have Wi-Fi. You don't even have to get connected. So this is only for small thing, and I'm giving you an assignment on the USB, how it encodes the data on these two wires. And you can read about it. It's a homework problem. So anyway, so this is an example of designing like mod 8. Mod 8, that's a huge, that goes from 0 to 256. If you have to draw a finite state diagram, it's gonna have 256 states. Okay, that's not, so we're gonna design from now on, all the future designs are not gonna be small, they're gonna be big. And for that, we're gonna use existing modules, tiles, we're back to tiles. Okay, and then the flip-flops are used for just storing data. Stores this data, adds a 1, on the next clock, loads the next number. So you see 0, 0, 0, 0, 1, 0, 2. And if you want to reset, this is an asynchronous reset. That means it comes from, if you remember, that comes from outside. This is the latch. That comes from outside. Look at the chapter 4. That is asynchronous, meaning this is the regular, this is run through clocking, the clock. So this is for normal operation. And then if you want to reset, it comes from outside. So that is for that. So this is a synchronous clear. So this is the mux. If you make it a 1, it's going to take the 0 and it's going to, on the next clock, it's going to set that to 0. It's going to load that. Now, this is where, so you do these things and then you put all this together and the tools is gonna look at all these equations and simplify it, and believe it or not, it will create, and because I'm incrementing, so this is an adder, I'm incrementing, it's always 0, 0, 1. So most of, so this is being an A plus B. But the B is 0, 0, 1, so it's going to simplify the circuit. It's going to look something like that. And you can, there are, chips that exist like that. Okay, let's see if we can finish this chapter. Okay, remember I said a little while ago that period has clock setup time, Q to clock to Q. And we're going to have another clock skew. There's another parameter that we need to add. So if you look at here, this clock gets to this flip-flop after long delay, wire delay gets into this one. So it is possible that this clock will click. This is a shift register. This is supposed to, every clock, if it arrives exactly at the same time, this is going to go over here, this is going to go over here, so it's going to shift, do the shifting. But if this clock gets here faster than this clock, then the shift is not going to work correctly. So this is going to go over here, and then go over here, instead of this going. Or it can go to this one first, and then that one first. So all of this summarizes into another parameters that we're going to give. It's called clock skew delay. These are again through simulation. So from now on, you're going to have 3 parameters: clock to Q, setup time. This is the propagation delay. This is the delay of the circuit. Like in this case, is 0.3 nanoseconds. That's the propagation delay. But for the flip-flop, we have setup time. We have clock to Q and clock skew. The length of the clock. So we want to make sure that every clock is not running too fast. So all of that is added. So I'm going to give you clock to Q. I'm going to give you setup time. I'm going to give you clock skew. This is the only thing you need to calculate. Here, the problem gives you this, but if this was a CLA, you have to figure out what the delay is and use that. Okay. Any questions? So don't miss the next chapter 6. We're going to go into a little bit more complex designs. Data path, we're getting ready for CPU. Okay, eventually we're gonna learn design miniature CPU.